This study compares vortex shedding from an airfoil for varying angles of attack. Vortex shedding occurs when a continuous fluid flows past an obstacle, creating a velocity shear. The Kelvin-Helmholtz instability across the interface of the differing velocities creates a pressure gradient, leading to oscillations in the flow. Vortices are formed behind the object and detached periodically. Shown here is the vortex shedding around a cylinder for a Reynolds number of 80. You can see the small vortices forming on the backside and periodically releasing. Expanding on this concept shows how vortices shed on the backside of an airplane wing. This contour taken from a single point in time shows a lift-induced vortex. Although vortex shedding is often most prominent at the tips of an airplane wing, vortices can form on the back along the entire length of the wing from tip to fuselage. A NACA 12 airfoil was used for the geometry in the study. The governing equations used in this analysis included the pressure-based or incompressible flow equations. The velocity, discussed later, justifies this assumption. The transient part of the equations must be included because the solution is not steady state. The equations can be simplified to 2D to improve computational efficiency. The simple method was used with second-order upwinding and realizable K-epsilon model to account for turbulence. The sweep method was used from the circular body surrounding the airfoil and rectangular body trailing the airfoil to generate a global mesh as shown in the upper right-hand corner. Inflation added 10 layers around the edge of the airfoil with 2.5 growth rate as shown in the detailed view of the tip of the airfoil on the left. Note the uniform mesh size, which is helpful when looking for vortex shedding. The right depicts the overall mesh scheme. Extra steps were taken to improve the mesh quality downstream of the airfoil in order to improve the accuracy of vortex shedding. To close the problem, the boundary conditions were defined by adding an inlet velocity of 200 meters per second and applying a no-slip condition on the wing surface itself. Standard pressure and density conditions compromised the surrounding environment. The solution will never reach convergence due to the unsteady nature of the Kármán effect and vortex shedding. However, examining the residuals of the solution provides some insight to the integrity of the solution. After about 45 iterations of each time step, the continuity residual, shown in white, decreases to magnitude 1 to 10 to the negative third. Note that for each time step, the residuals jump back up again. Here is the U component of velocity over the airfoil at an angle of attack of 4 degrees. Notice the smooth flow over the surface does not seem to produce noticeable vortex shedding on our scale of interest. Now let's examine the 8-degree angle of attack and slow the animation down to better see what's happening. Notice the vortices are now forming on the backside of the wing. The blue areas mark the calm, slow moving center of the vortex. The color gradient moving radially outward from the center depict the increase in velocity magnitudes towards the outer edges of the vortex. Switching to the 12-degree angle of attack shows a decrease in frequency of shedding compared to the 8-degree. However, when the vortices detach from the wing, they are far more prominent, thus providing more drag on the backside of the wing. With the increased angle of attack, vortex shedding off the backside of the wing becomes more intense. Remember, the first simulation of the cylinder shows the vortices detaching from the top and bottom of the cylinder in a uniform manner. With the airfoil, the vortex formation seems non-uniform from top and bottom. Also note that as the angle of attack increased, the vortices shed became increasingly more powerful. Further areas of investigation may include expanding the analysis to 3D and adding winglets on the ends to see how vortex shedding is affected.